My name is Ms. Leminski, and I am going to be in charge of leading you through some videos for topic or chapter 2, where we'll be looking at quadratic functions and equations. Today we're going to start with section 2.1, and we're going to talk about the vertex form of a quadratic function. The objective for today is that you'll be able to identify key features of quadratic functions. So I would pause the video. In my lessons, I like to put the little pencil up here if it's something that you should be writing down. So for me, I always like to have those objectives in my notes, especially when it comes to studying. So identify key features of quadratic functions. Anytime you need to pause the video to write, please do so and then start again. You don't need to write this down, but this section is broken into 2 days. Today we're going to focus on transformations in vertex form and then key features given vertex form. So the vertex, axis of symmetry, maximum, minimum, domain, and range. Before we begin, I wanted to just look at this little activity. It says the table represents a of x, the area of a square, as a function of side length, x units, where x is a positive real number. And if we look at the table, we can see that if we have side length of x, and we have a square with side lengths x by x, we would want to be able to find the area of a square. Now, in order to find area, hopefully you remember that it's length times width or base times height, so x times x equals x squared. So that would be the equation or function to represent area. Having said that, if it was side lengths of 1 and 1, 1 times 1 is 1. Side lengths 2 by 2 would be 4. 3 times 3 would be 9, and 4 times 4 would be 16. So it says consider the function where the area in the tables are doubled. Write the equation of a function that represents this. In chapter 1, we talked about how we can adjust functions. So in this case, we have a of x, and if I want to double the area, that means I want to double the output. In order to double the output or the y values, I need to multiply by 2, but it needs to be outside of the grouping symbol. Now, having said that, whether I had those parentheses there or not, it wouldn't matter, but I should get 2x squared. Part B says look for relationships. Graph the ordered pairs for both a of x and your new function. Okay, so if I graphed a of x, again, that's 0, 0. If I plug in 1 for x squared, I get 1. If I plug in 2 for x squared, I get 4. The nice thing about parabolas is because they're symmetric, as soon as I have a point at 1, 1, I could just reflect that across this axis and get a point and reflect this across. So this purple curve would represent a of x. And actually, I'm going to go back and change this function, and I'm going to call it f of x instead of a, so that we have 2 different function names. If I want to graph f of x, I would have to do 2 times x squared. So if I plug in 0, I'd get 0 times 0 is 0. If I plug in 1, I get 1 squared times 2 is actually 2. Again, reflected across. And if I plug in 2, 2 squared is 4. 4 times 2 is 8. So that would actually be way up here. And what we can see by doing this activity is that when we doubled the outputs, or the y values, we get a steeper graph, which is a vertical stretch, which you talked about last chapter, and we're going to review that today. Last but not least, it says find the equation of a function whose x values are the same as a of x, but whose y values are 2 units greater than each. Okay, so now we're back to talking about the y values changing. So if we call this g of x, which means I don't change the x at all, so I leave the x squared. And if I want to increase them by 2, that would mean I'd have to add 2 onto the end, not group with the x. So again, this is a little bit of an activity to remind us of what we learned last chapter about what happens to functions when we multiply and add. And it also introduces this idea of the quadratic, which is x squared. And the shape of the graph is a parabola. Okay, now let's get into a quadratic function. It can be written in the form f of x equals ax squared plus bx plus c. And just so you know, this would be considered standard form, and we're going to go back to that in the next few days. But for right now, it's an introduction. Anytime we do transformations of the parent function, I often get the questions of, Ms. Leminski, I know we're transforming the graph, but what am I transforming? You're transforming the parent function, which is f of x equals x squared, just that very basic graph that we'll look at in just a second at the bottom. The graph of any quadratic is called a parabola. It's that U shape. And then finally, today we're going to focus on this thing called vertex form of a quadratic function. And that looks like f of x equals a times x minus h squared plus k. So we're going to look at it in a different form than what we wrote in the beginning for standard form. The reason vertex form is nice is because this h and k value tells us exactly where the vertex is. So hk is the vertex, but we're going to connect that to how we can understand it based on translations, translating the graph left, right, up, and down. Okay, so before we move ahead, let's look at that parent function. Again, we're focusing on the graph f of x equals x squared, because as we do transformations, we're always transforming that graph, that parent function for our quadratic. So here it is. Again, we said it's got a point at 0, 0. It's got a point at 1, 1, and 2, 4. Therefore, it has a point at negative 1, 1, and negative 2, 4. The vertex is that point where it changes directions, and it would be 0, 0. Axis or line of symmetry is the line that cuts the graph directly in half. So if we're talking about a parabola, it could flip upside down, but they're always going to be either up or down, so it's always a vertical line. Vertical lines are x equals whatever x value it cuts through. So x equals 0 in this case. The reason vertical lines are x equals is because for every single point on this line, the x value is 0. You're going to have to be able to identify minimums and maximums. Now that's a height. So I find the lowest point, since it's a parabola facing upward, and its y value is 0. So the minimum here is 0. Domain we talked about a lot last chapter. If I look at this graph coming from the left, it goes left forever, so it goes to negative infinity. It is continuous, okay, so if I chase it with my pencil, I don't have to pick it up at all. And then it keeps going on forever to the right. So it's from negative infinity to infinity. And finally, the range. I look at the graph from bottom to top. The lowest value is that 0. It is a point on the graph, so I use a bracket. And finally, it goes up forever because those arrows go up, so it's 0 to infinity. Make sure you get all that down. If you need to pause the video, do so. And then we're going to move ahead and talk about transformations. You don't have to write anything down on this slide necessarily. You may want to pause and take a few notes on things that you need, but we will actually write it down next. Having said that, these are the rules that basic rules we use for all functions. You used them and learned them last chapter. And really you want to focus on is something affecting the x value or the y value. And if it's grouped with the x, so grouped with the x, it affects the graph horizontally always because it's on the x-axis. And the other key part is that it's the opposite of what you think. Okay? So if it's addition or subtraction and it's grouped with the x, it's going to move the graph left or right opposite of what you think. And then if it's multiplication or division, it's going to be a horizontal stretch or compression opposite of what you would think. So if you're multiplying by a 2, it's actually a compression. If it's outside the grouping symbol of x, that means it's affecting the y values, or it affects it vertically. And in that case, it's the same as what you would think. So if you see something being added or subtracted after the x part, then it's going to shift the graph left or up or down, the same as what you would think. So a plus 2 would be up 2. If you see a multiplication or division outside of the grouping symbol with the x, then it's going to be a vertical stretch or shrink. So if it's a 2 times that, you would be a vertical stretch by 2. It's the same as what you would think. Okay, this is where you can write some of that information down. Again, we're focusing on vertex form. The only thing that's grouped with the x in vertex form that's important to know is this minus h. Okay, so the x minus h is grouped with the x, therefore it's a horizontal translation of h, but the opposite of what you would think. So if this is a minus 2, it actually goes to the right 2. Then we could look at the plus k. That is outside of the grouping symbol with the x, so this plus k is going to affect it vertically, so up or down, as you would think. So again, if it's a plus 2, it moves it up 2. And last but not least, the a in front of the parenthesis means that it's multiplication outside of the grouping symbol with X, which means that it's going to be a vertical stretch or compression. Okay, and again, it's the same as what you'd think. So if it's greater than 1, it's going to be a stretch. And if it's less than 1, it's going to be a compression. And actually, I'm going to say if it's between 0 and 1, because as soon as A is negative, it's going to flip the graph. So we're going to think about that separately. It's going to actually flip it upside down. Okay? So pause the video, make sure you get those down, but those are the main transformations we need to understand about graphs. Now, when I look at these two examples, okay, so we're going to look at examples, and again, make sure you get these in your notes. First, we're going to look at g of x equals negative 1/2 times x plus 2 quantity squared. Okay? Now, the biggest thing I want to make sure I know is that this negative outside, it's going to open the graph down. So it's going to be upside down. Okay? Then I can work across, and next I have the 1/2. Because it's outside, it's going to be vertical. Because it's multiplication, it's going to be a stretch or compression. And because it's less than 1, it's a vertical compression by 1/2, by a factor of 1/2 if you want to use that wording. And then last but not least, I see the x plus 2, which means the plus 2 is grouped with the x, so it's going to go left or right, opposite of what I think. So I see a plus 2, so it's actually going to go left 2. Now, the other option, we could have just thought about the vertex. Okay, so I'm going to put a little star here. The vertex of this, remember, is hk. But h has to be the opposite of this. So it would be a negative 2. And because there's nothing on the end, it's like a plus 0. So it shifts up 0. So these two things are going to actually help you find the vertex the same way. Now, when I go to graph this, here's my recommendation. Plot your vertex first. Okay, so I would take from the parent function that key point at 0, 0, and I would shift it left 2. I'm not shifting it up or down at all, so I'm just going to plot my vertex there. Having said that, I could either use this or that translation like we talked about. Now, in order to get the rest of the points, I want 5 points. You could think of it a different way, but until you get to a higher level, I actually just encourage you to make an XY chart and pick a point right next to it. So here's negative 2. I'm going to pick negative 1 and 0 for my table. I only need 2 other ones because, again, I know they're symmetric, so I'm just going to reflect those points. And then I plug them in. If I plug negative 1 in, I get negative 1 plus 2 is 1. Next I do exponents. 1 squared is 1 times negative 1/2 is negative 1/2, which means at negative 1, I have a point at negative 1/2. I reflect it, so also at negative 3, negative 1/2. Now I plug in 0. 0 plus 2 is 2. 2 squared is 4. 4 times negative 1/2 is negative 2. So I have a point at 0, negative 2, and therefore I reflect it. I also have a point at negative 4, negative 2. Okay, so when I look at that, it would be a little wider than the parent function. A vertical compression makes the graph wider because if you push down on it, or up on it in this case, it flattens it out a little bit. Okay? All right, go ahead and let's look at the second one, I guess. We'll do one more together. Okay, we'll go a little bit quicker. It's going to open up because the 2 is positive. Because the 2 is outside, this time, because it's bigger than 1, it's going to be a vertical stretch, so it's going to be skinnier. The x minus 1, because it's with the x, it's going to shift it left or right, opposite of what you'd think, so it's actually going to be right 1. And this one now has the minus 3, so that's actually going to move it down 3, because it's not with the x, so it affects it vertically as you would think. Again, the other thing I could look at is that this minus 1, negative 3 actually tells me that the vertex will be at negative 1, positive 1, sorry, negative 3. All right, when I go to graph it, again, I could take that point that was at 0, 0, and I can go right 1, down 3 using this language, or I could have just used the vertex and plotted it. To find my other points to show the open upward and vertical stretch, again, I encourage you just to use an XY table and pick just two values. It doesn't matter, it'd be 2 to the left or 2 to the right. I'll pick these next two values to the right. So since that was at 1, I'm going to test 2 and 3, and then I'll reflect them. So if I plug 2 in, again, order of operations, 2 minus 1 is 1, 1 squared is 1, times 2 is 2, and then minus 3 is negative 1. Okay, so I have a point 2, negative 1. And then if I plug in 3, 3 minus 1 is 2, 2 squared is 4, 4 times 2 is 8, 8 minus 3 is 5. So I have a point at 2, negative 1, which means I also have a point at 0, negative 1. I have a point then at 3, 5, which also at negative 1, 5. And I can see that it's a little bit skinnier and open upward. All right, this graph, this is what we just did, but this shows how it compares to the original. So these show the parent function and then how it shifted, and it gets skinnier in this one and it got a little bit wider in this one. All right, now I want you to pause the video and try these two on your own. And then once you're ready, play the video and you can check your answers. So hopefully this is what you got. Number 1, you should have seen that it opens down because of the negative, and then 2 left because of the plus 2. When you graphed it, you should add your vertex at negative 2, 0, and then you could have checked a couple of points to get the others. The second one, there's no number in front, so it still opens up. Neither one of these had a stretch or shrink or compression, but this one, because of the minus 1, was 1 right and up 2. So my vertex was 1, 2, and then you could have used the table to plot the other points. All right, now that we understand how to see the transformations and sketch a graph, now we're going to talk about all of the key features of the quadratic function. Okay, so again, we can start with graphing it. I always start with what we talked about. This 2, it's going to be open up because it's a positive 2. Because it's outside and greater than 1, it's a vertical stretch, so it's going to be steeper by 2. And then last but not least, the minus 3 is going to make it to go to the right 3, so left or right opposite of what I think, and then the plus 4 is going to go up 4. When I go to graph it, that means I would take the point that was at 0, 0, I go right 3, up 4, right 3, up 4, which means my vertex is at 3, 4. If I make that table, in this case, I'm going to pick these 2 points to the left, so I'm going to go 1 and 2. 1 minus 3 is negative 2. Negative 2 squared is 4. 4 times 2 is 8. 8 plus 4 is 12. Okay? Way up here somewhere, okay? And then, so that's, I actually did 1 first, so that's 112, so that would be 2 over. That's why I was getting a little confused. I couldn't figure out why it was so high, but then when I plug in 2, I get 2 minus 3 is negative 1, negative 1 squared is 1, times 2 is 2, plus 4 is 6. So this point is at 1, 2, 3, 4, 6. There we go. So those closer ones. There we go. So it's still a little bit steeper, and those are my points. So usually I flip these. That's what caused my confusion. Okay, axis of symmetry. We already talked about it. It's the vertical line that cuts it in half, which means it's always x equals. And here's the key. It's x equals 3. It's always vertex. Okay? On the same note, because it's going opened up, it's going to have a minimum. It's this value right here. Well, here's the key again. It's always going to be the y coordinate of that vertex. Last but not least, domain and range. Once again, left to right, arrows on both sides, everything in between. So your domain is negative infinity to infinity. All parabolas, all quadratics actually have the domain of negative infinity to infinity. And finally, range, looking bottom to top, it starts with the lowest value of 4. It's a point on the graph, so I include it, and it goes up to infinity. So yes, your minimum or maximum value will always be a part of your range, but you do have to be careful because if it flips upside down, it changes it slightly. All right, I want you to try this one. Again, pause your video, try it, and then when you are done, come back and see how you did. Okay, so for this one, again, I would see that the negative, it's going to be open down in the end. The +4 moves it left 4, and the -5 is going to move it down 5. So when I go to graph it, I took the point at 0, 0, left 4 down 5, which makes that vertex at -4, -5. I then plotted my next 2 points, so at -3, -2, I ended up with the point -3, -6, reflected it, got that point, plugged in -2, got -9, reflected it, so that's what my parabola looks like. Having said that, again, the axis of symmetry is x equals -4, the maximum this time. Okay, so the highest value on the graph is at -5. Domain, like we said, is always -infinity to infinity for parabolas. And now we have to be careful because range, if I come at the graph from the bottom, the first thing I hit are these arrows going downward, which means it goes down to -infinity. Remember, interval notation has to be smallest to biggest. So it goes down to -infinity, and then the highest value is actually the -5. So you do have to be careful with the range with parabolas, depending on the direction it goes. Okay, so that's the end of day 1. You can now move on and attempt your Pearson practice for day 1. Tomorrow we'll watch a video on day 2, which you can see is writing the equation in vertex form, given the vertex and another point, converting from vertex to standard, and writing the equation of a transform function.